Thank you very much for the introduction, and thank you very much to the organizers for inviting me here. I didn't have too much, unfortunately, with Professor Nekovar. I only went some dinner with some other people, but I had the impression that he was a very kind man, and it's always very sad to lose people especially when they're young. So let me start from my result. As a setting, let A and M, this is a regular local ring, on which a group G acts. This is assumed to be finite. And I also assume some, and I denote by I sigma, which is just A minus ideal generated by this. Or in other words, you can say that the spec of A over I sigma is equal to the fixed point, scheme theoretic fixed point of the sigma.
So this is the ideal generated by this.
Oh, yeah. Or in other words, if you want, this is x cross x over x, this is delta, and this is gamma of sigma. And we assume two conditions. The ring of fixed points is Noetherian. And this A over AG is finite. And also, that's three conditions. So for any sigma in G not equal to 1, this A over I sigma is a finite length as a module. And finally, AG over AG. So I have a natural map like this. This is an isomorphism.
So actually, the condition that AG is Noetherian and A over AG is finite are actually.
Yeah. Okay. Yeah. It might be redundant.
Of Nagata Ikin.
Yes.
Noetherianity and using trace maps, you get also finite as usual proof of finiteness.
Yes. Yeah, it could be redundant, sorry. I just copied from a paper of Serre, I guess. And define function, G to Z. I denote by AG, which is defined as follows. I can write it here. So AG of sigma would be minus of this length of A over this guy when sigma is not equal to 1. And if it is 1, I want to make it the character just 0. So AG sigma for sigma equal 1. Conjecture, rather old and minor conjecture of Serre, 60. I think it's 60. So let's fix some prime number, which is invertible in A. Then first of all, AG is a character of a QL representation, QL bar representation of G, of course. And secondly, this is QL rational. Right?
This is something you proved in the DVR case, right?
Exactly, yeah, that's what I'm going to tell you. Theorem. So my theorem today is that this is true. When FB in the equal characteristic situation. And let me talk about the history. As Bruno said, yes, when A is DVR, namely dimension of A is equal to 1. So this AG is a classical Artin character. And the theorem is conjecture is in core local. I hope my spelling is correct. Okay. So
also the Q rationality is
yeah. Q rational, no, not Q, right? QL rationality. Yeah. I think it's in Korelko, no? And anyway, somewhere in Serre's. Yeah, it's somewhere in Serre's work. When dimension is 2 in the equal characteristic situation, this is proven by Kato and Saito, Shuji Saito, and Takeshi Saito. Okay, and when the dimension 2 in mixed characteristic situation, characteristic plus some condition, under some condition, then it's Ahmed proved it. And later, didn't go up. How can I manage? Oh, there's no hole.
This in here.
Ah, yeah, okay. Did it go? Yeah. Well, okay. And lastly, in a mixed characteristic situation, in dimension A is equal to 2, in 1, mixed characteristic is announced by Kato in his ICM address, but actually written down by Kato and Takeshi Saito. Wrote a proof. I don't know if Kato ever written down the proof of his. Okay, so today I want to convince you that this theorem is not that hard anymore after development of a theory of nearby cycle over general basis. So idea of proof. Excuse me? As far as I know, I don't think they're proving the rationality. They're only talking about the QL bar part. At least, I mean, I looked at this Kato's work, and he said that he proved this Serre conjecture, but he only announces this the construction of representation as QL bar representation. So
there is also the trivial case where the order of G is invertible in the residue field, where you get augmentation representation.
Mm-hmm. Excuse me?
The characteristic 0 case.
Probably. Yeah, I didn't think about it. Okay, so let me tell you the idea of the proof. So Kato and Saito. So today I don't treat this much generality, but Kato and Saito reduced this conjecture to the geometric situation where A is essentially the case where A is essentially of finite type over K, which is algebraically closed. And of course, it contains FP. So I only consider this geometric case. Of course, this reduction needs some argument, you know, like Artin approximation, etc., but etc. But okay, don't ask me too much. It's a work of Kato and Saito. And let me fix a notation. As usual, psi. I fix a psi, which is a character. Non-trivial. And I fix for my the rest of my talk. Then I can consider the Artin-Schreier sheaf. Artin-Schreier on A1 of K. Okay. So if I were given some morphism from a variety to A1, let's call it F, morphism, then I can consider, I denote by LF, I love F, which is simply the pullback. So this is kind of exponential F, but so by sort of spreading out argument, the first part of the conjecture would be reduced to the following theorem. So this is pretty much geometric now. So let X be a X be a morphism variety. This is F. X is regular. And I have closed point. This is finite type now, on which G acts over A1. This is X, G acts on X over A1. So for any sigma, X going to X over A1 commutes. So this is what I mean by. And F is finite type and flat. And the fixed point is just so this is as a set, So I'm just rephrasing the conditions of this, the initial condition. Okay. But I'm just spreading out a little bit so that X is finite type over A1 now. And I assume that X restricted to X minus X is smooth.
And GX trivially on A1?
Yeah, GX trivially on A1. So yeah, you can say so. GX trivially on A1, and this map is, this morphism is G equivariant. Yeah. And then I can consider F times T prime. I'm introducing some other parameter. This parameter has nothing to do with this. So I call this coordinate T, and I'm introducing another new coordinate, T prime. So this goes to A1T times, so I'm doing something very close to Fourier transform. And I have a map mu. This is a map sending xy to x times y. So I have this composition. So this is F cross the identity. Okay, so I have this A1 T prime line, and I have this x direction. I can consider on this x cross A1 T prime the sheaf L shriek of F T prime. So since this is from x cross A1 T prime, sorry, I want, what's this? I completed by P1. So this streak means that since this is from A1 x cross A1 T prime, a priori, this at infinity, this sheaf is L of Ft prime is not defined, but I extend by just by 0. So I have some sheaf on this P1 line, P1 cross X.
Infinity prime.
Infinity prime, exactly. Exactly, that's better. And my claim is that minus AG of sigma is equal to trace of sigma, which, whoa. So I have psi of PR prime, L shriek, FT prime, X comma infinity prime. Yes. So PR prime is this direction. So this is PR prime. And I'm taking some nearby cycle around this point, X comma. So X is some point. The closed point I'm fixing. Okay, so that's a fixed point, isolated fixed point of this action of G. And I'm taking the nearby cycle around this point. This is just a line, so this is just normal nearby cycle. And yeah, I take the stock at here, and because this is G equivariant, we have the action of G on this nearby cycle. And the trace of that would be this. So in some sense, sigma is not equal to 1. So except for this condition, this is a representation that we're looking for. Okay, even though it's QL bar, it's QL bar sheaf, or you can go. So here, I have to take that this guy is at most QL beta P sheaf. So at least this rationality is achieved by this equality. Is it okay? Okay, I can erase this. So let me show you how to prove this theorem. Well, in fact, this theorem, I didn't find out this representation, but in fact, if you read this Kato and Saito paper, the representation is almost there. But it's written as a conjecture. They say that this is the representation, but here's the conjecture, and that's almost the form of their conjecture. So I have two ingredients. First, I have two things. Relative Lefschetz Verdier pairing. So what's this? Let X over S would be separated, finite type, Noetherian, if you want. And fix some F in the derived category with constructible sheaths, which is universally locally acyclic with respect to this over S. So I think most of the people don't want to use this kind of notion, but I can't avoid. But what it roughly says is that, so if it is a smooth sheaf, you want some sort of smoothness. So, but smoothness is a very strong condition, but you can make sense of, if you're given some sort of vibration, it makes sense to talk about the smoothness of with respect to this direction, so if S is equal to X, then being universally locally acyclic with respect to this identity is the same as the smoothness. But somehow it's relaxing some sort of smoothness with respect to this direction. Okay, that's the rough idea.
It's locally constant when X is S.
Oh, when yeah, locally constant, locally constant. When when X and S are the same, then it's locally constant. Okay, so anyway, this is sort of smoothness condition with respect to this vibration. So I assume I have some morphism. It can be a more generally cohomological correspondence, but yeah, I don't want to go into too much complicated notation. So I just consider in this kind of situation that F is sort of equivariant. Under this assumption, Liu and Zhang.
What was little f?
Excuse me? You're right, you're right. So X. This is also given, right? So yeah. At the end, we want this F to be the sigma, but yes, yes. I'm given some morphism. An endomorphism of X over S. Thank you, thank you. So they associated this to this alpha. I denote by tau S of alpha, which is a class of xf. This is equal to x times x cross x, x. So it's a fixed point of x, a fixed point of f at the canonical. This is dualizing complex, relative dualizing complex. So this is called a relative Lefschetz fairly appearing. Okay, so in the case where S is a point, this is written in SGA5 by Luke, and Abe Saito is saying that this is really related to a sort of Swan conductor. But I'm not talking about the relation with Swan conductor today, but the theorem that I want to use, the one in Liu and Zhang, is that this S of alpha is compatible with phase change. What does it mean? So I assume that I'm given some diagram like this. I have the space change diagram, okay? Recall that I have F here, and also this an endomorphism F. So I can pull it back because it's a universally locally acyclic. This pullback still remains to be universally locally acyclic with respect to this morphism. So like, okay. So this is Ft, the pullback, and also I have Ft here. And by playing with some adjunctions, you can show that, you can see that we have a canonical map from xf of k xf over s going to the pullback. xt ft k of xt ft over t. There's a canonical map, restriction map, I would say. And here I have this tau. And alpha can also be phase changed. And here's tau T of, I call it G. G upper star of alpha. And via this restriction map, this pairing is sent to this point.
So do they work with torsion coefficients?
Yeah, that's a kind of subtlety, but yeah, you're right. Here, I think for this theorem, I don't need it to be torsion. Wait.
Because anyway, to formulate the theory of universally locally acyclic.
Yeah, yeah, you're right. I mean, I have to go back and forth with the torsion and the QL sheaf, so that's why I didn't specify what kind of situation I was. But anyway, yeah, you're right. That's a kind of subtlety. And I think this theorem was stated for torsion sheaf, I believe.
Is it in the work on categorical trace?
Exactly. So they use some sort of modern technique of categorical trace formalism to show this theorem, and it's very beautiful, in fact. But I believe that the theory, if you just want the proof itself, I think if you draw a very, very big diagram, then I think it's possible. So this is, I believe the theorem itself is very, very traditional, even though the way they proved it is very modern. But I think we can reprove in a very traditional way. So I wouldn't be surprised that this was written in SGA5.
But their proof is much simpler.
Yeah, exactly. Yeah, exactly. Am I doing something complicated? Whoops. Okay, so that's the first ingredient. I think I'm talking too fast. So second one is a sort of universally acyclization. You'll see what I mean. I think this is also more or less known to experts. Okay. So the situation is similar. I have X2S, and I have some open. This is open dense. Yeah, for here, I really need lambda. I really need the sheaf to be torsion. But anyway, assume given Fu on Xu, which is Fu universally locally acyclic. So this Fu is universally locally acyclic with respect to Fu, and I'm not talking about anything outside of U. Then there exists T which is an alteration. In G on X cross T such that the following two hold, such that, morally speaking, it's after pulling back on U, it's the same as Fu, and outside this is extended by by universal locally acyclicity outside of this locus of U. That's Artin. By the way, it's really essential to work in derived category. So this guy, if this guy is in the bounded derived category of XU, even if you start from sheaf, this may be in the derived category. So it's really essential to work in the derived category, such that if G, first of all, G is Ft universally locally acyclic. So, and it's an extension of Fu. So if I restrict G to xt cross T U, then this is nothing but just a GU. And the form I need in the proof of the theorem would be that I also need to put some equivariant equivariance of this Fu. So also this, if you were I were given some correspondence, then it has to be extended to G. But that's essentially, that works essentially the same proof as this lemma, so I didn't.
Kind of that classification?
Yeah, it's that part is contained in the Orgogo theorem, in fact. It uses sort of flattification, but yeah. So yeah, the idea of the proof is as follows. I don't go too much into the detail of use of Orgogo theorem on nearby cycle over general base. So here, what I use is so in order to so there's a notion of nearby cycle for general base, and one of the most important property is that this nearby cycle commutes with base change. And what Orgogo theorem, there are two Orgogo theorem that I'm using. One is that we can make sheaf good. Good means that nearby cycle commutes with base change. And secondly, under this condition, nearby cycle is constructible. So in general, this nearby cycle over base change is kind of crazy object, and it can be it's not in general constructible at all. But that's an observation by Bellini, I believe. But once it gets to a good situation, then the nearby cycle is constructible. Then it's constructible. Nearby cycle is constructible. So morally speaking, what I do is that I go from, so I consider the limit of all the alteration of this guy, and then by Orgogo theorem over there, I just, so I take the, let me write it here. So I start from S. I take, it's not really a Zariski space, but I take all the alterations. T, and on here I have a generic point, and I have eta to S. J, let's call it J. Then I can consider J lower star of R of F. F pulled back to this eta. Okay, and this has to be the universally locally acyclic sheaf that I want to find, at least over this ideal space. then in order to go back to the normal world, finite type world, I use this constructibility to descend. That's the idea.
But I think in fabric, you could use just modification instead of alteration, but here you need alteration.
Alteration is true, yeah. That's in order to achieve this universal locally acyclicity.
But in his paper, the modification was enough to...
So when you start from... Yeah, so when I start from when... let's see. So when I start from FU shriek to everywhere is good. If this is good, then I can make this alteration by finite morphism. Mm-hmm. So I use orgogo first to make it good, and then I take a finite morphism, finite cover to make it universal.
Shriek, you say.
This is extend 0 to S. Okay. Yeah.
So once it is good, then
again.
Yeah. Exactly. So if you're in a good situation, then finite cover is enough. So I use these two ingredients in the proof of a theorem. So the idea is that the theorem of Liu and Zhang is sort of a continuity property of this. So the idea is that we are given some sheaf, this sheaf on this this x cross P1, and it's parameterized by P1. And somehow, whoops, this equality is somehow saying that if you restrict this family at 0, then you get some AG of sigma. And what I want to show is that if I restrict this family to here of that left-hand variety appearing, then I get AG. And if I restrict that to infinity prime, then I get this trace. That's the idea. But of course, in order to achieve this idea, I need this universal locally acyclicity. And that's where I use this lemma. So let me... Yeah, I'm talking too fast, sorry. So I have this situation here, okay? P prime. And I considered some sheaf, ft prime, okay? But that's universally locally acyclic on A1, so on here, this is universally locally acyclic. Okay, so use this lemma to produce some alteration, but here it's just a curve, so it's just finite morphism. Let's call it T. So that there exists some L tilde. If I restrict L tilde to this, this is going just to be the pullback of L ft prime, and L tilde is universally locally acyclic with respect to this PR prime T.
Just to check, it's P cross P1 over X.
Ah, yeah, wait, so, exactly. So T X cross T cross, so it's a P prime A1. I think, yeah, oh no, it has to be. Yeah, and yeah, sigma is acting on here. Well, the way I do is I fix one sigma, and I just want to show this this equality. So if I fix one sigma, then as I said orally, that lemma can be upgraded by also considering this sigma equivariance. So this can also be extended. This sigma's action can also be extended to L tilde. And then I want to draw some diagram, as usual. H naught of x sigma times t, and k x sigma times t over t. This is where this using relative Verdier trace, Verdier pairing lands in. So this is tau t of, I call this, so I have this sigma. I call it alpha. Okay. I have two restrictions. One goes to, yeah. I want to, so there's one and infinity here, 0 prime and infinity prime here. And I want to fix any lifting, which I denote by what did I do? T0 prime, and T infinity prime. This is just some lifting. You can, since it's alteration, I can take some lifting of it. It can be any one. Then I can restrict this T to this T0 prime, K, X. So this is just and also the same for the infinity. Oh, sorry. And now, Liu Zheng's theorem is saying that this is equal to this. This will be sent to tau of T infinity prime alpha. Okay, now I'm taking sigma not equal to 1. So by assumption, the fixed scheme, this guy, is just equal to x. Okay? So this is just, at least the underlying scheme is equal to these. So because the Tau homology doesn't see any nilpotent difference, this is isomorphic to lambda, the coefficient of the sheaf. So this is, so these are because sigma is not equal to 1. So what it says is that these guys are the same, at least in this lambda. So finally, I can conclude my argument. This is really hard to organize. Very sure. Is it okay? Yeah, so finally I just want to compare the two sides of this. So the left shot variant appearing for t0 prime and t infinity prime, and they're the same as those things. So namely, what I had with that argument above is that this t0 prime of alpha is equal to in lambda, and then t0 lambda. So roughly saying, so t0 prime is something on this line, right? Are there any? So this is the tau 0 line. And here's a tau t infinity prime line. Yeah, of course, I'm taking alteration to make it universally locally acyclic, but that's the and this t0 line, it's pretty easy to compute because this L ft prime is smooth, or in other words, it's locally constant, or locally constant. So in this situation, it's just this is. If I restrict to 0 line, I plug in this t0 to t prime, and this is just constant sheaf, right? So I take just a constant sheaf, and this guy would be just a left shot variant. So tau t0 alpha is left shot variant appearing of this canonical. So this is equal to L ft prime times 0. This is isomorphic. This is since 0 times f is 0, so it's constant sheaf. So this is equal to the left shot variant appearing of this sigma, and this is computed in SPA5. So it's equal to length this is nothing but minus ag of sigma. And the other side, so this dimension of t is equal to 1, or I would say p prime. I should have said it. P prime is equal to 1 by delaying finitude. This L freak ft prime is good with respect to PR prime, or in other words, this nearby cycle, the classical nearby cycle, the one that I'm using here, at around infinity. Around infinity of this guy would become the same as L tilde restricted to x cross t infinity prime. So when the scheme is dimension 1, nearby cycle always compatible with space change. So I use that. And when you have a universally locally acyclic family over some curve, then it's just a nearby cycle is exactly just a restriction to your fiber. And by some, in Katslan 1, this guy, this is supported on X.
And there is also a perversity effect here.
Exactly? Oh, excuse me?
There is also perversity. It's also a perverse.
Perverse. I'm not sure if I'm using that. Where?
Because if you want to get actual representation, not a virtual representation.
Mm-hmm. Ah, yeah. That's coming into the next step. Yeah. Okay, then, yeah, combining this, it's just supported on X, and you have a sigma is acting on this guy. So let's just verify the trace is just a normal trace at that point, this guy. So I get this theorem. Is it okay? Right, so in order to, so this, as Copper said, is, yeah, you need perversity or some sort of thing to say that this is actual representation, but also this is just QL bracket Z up to P representation, that rational representation, okay? So what I promised you is that I can show also the QL representation and how does it work. I'm not going to talk about the detail of this part, but the original conjecture of Kato and Saito that induces this Serre's conjecture is in fact slightly different form, namely they didn't use this sheaf. So the original, in order to achieve QL rationality in actual representation, the original Kato and Saito conjecture was saying that AG sigma is equal to trace of sigma, not this nearby cycle, but some sort of so-called total dimension representation of the vanishing cycle of S comma, what is this? X? Wait, this has to be S. Wait, lambda, where S is, so I'm taking this vibration over A1, and X is sent to S. Well, I should have normalized so that this S is equal to 0. But anyway, this S is just the image of this X. The original Kato and Saito conjecture was of this form, and they say that if this is true, then the Serre's conjecture is true, including the rationality. And this total dimension representation is so I have the inertia action here, inertia action, and taking into account this inertia action, I can cook up a Swan representation of this representation plus the identity one. That's the total dimension representation. So this is total dimension.
You mean you take home from this to the representation?
Excuse me?
You take the I invariant.
Yeah. So considering this action, yeah, I need this inertia action to define this total dimension representation. Yeah. So total dimension representation is QL rational. If you start from that's by Forlockel's result. So that's a rationality of Swan representation. So this is QL rational. This doesn't. In this form, it doesn't. They don't use any Artin-Schreier sheaf. This is just a vanishing cycle of the constant sheaf. So this is obviously QL rational. So what I have to do finally is to compare this guy and this guy. Okay. So finally, I have to do the final thing I have to do is to the final thing. So we need to show that this PR prime of L of x infinity prime is equal to the representation. So in order to achieve this, this is a corollary. This is a corollary of Lomon's geometric construction of Artin representation. Namely, in the case where, in the case x is of dimension 1, this is exactly the result of Lomon, who showed that the local Fourier transform of certain sheaf is coincide with this Artin representation. And I use that. It's just a small argument using this to upgrade to the higher dimensional situation. And yeah, then I can achieve this QL rationality. Thank you very much. That's it.
Are there any questions or comments?
So the next, the last step, the E8 from.
Oh, this is not just, yeah, it's almost essentially the same thing that in the first section of your Tom Semas DD article. It's just, yeah, of course, after this, yeah, we expect to show this mixed characteristic situation using Schultz's thing, but it's, I'm not competent to do that much. So.
I have a question, but first it's not directly related, and I don't know if it's mathematical or philosophical. But Serre has two observations.
Mm-hmm.
In the classical case, DVR, he shows that the Artin representation in general is not defined over R or over QP.
Exactly.
On the other hand, he shows that there cannot be a vague cohomology with these coefficients over a finite field because of the suprasingular elliptic curve. So for some time I thought, well, these two things are obviously related, and then I realized, no, I don't see that. So do you have any insight about this?
I don't know if it is related, but if I think the same thing works in the p-adic setting. So if you extend not QP to some W of K, I think the same thing should work. But it's technical, then I didn't carry out. But
yeah. So following this thing of Serre, one of the earliest work of Fontaine, I think, was proving that the Artin representation is defined over the bit vectors, I think. As far as
There's also work by Fontaine on this. Yeah.
the question is whether this has a crystalline. So you are saying that you have, in theory, you could have a crystalline version of this. For
Exactly. Yeah. I'm not saying that I can prove it, but there should be. Yeah, there should be.
But for DVR, just for the case of I don't remember. So for the case of DVR with perfect residue field, let's say. So was it Solomon constructed geometrically the QA, but was there a reconstruction using crystalline cohomology for DVR or?
Even in this QL case, I reduced to the DVR case.
No, but in the DVR case, where Lomon constructed the...
You mean Fontaine? Lomon did it?
No. Lomon did for QL cohomology.
Oh, yeah.
But for crystalline or something like this.
He did it, no? You did it.
What?
For the DVR case, the p-adic DVR case, I think it follows from my work with Adriano Marmora.
Okay.
Yeah. In the DVR case, yes. But in order to upgrade that to higher dimensional, it's more technical.
But that is some philosophical questions. So here we work with usual intersection, right?
Mm-hmm.
Fixed point. So nowadays people look at that down. So we should look at derived intersection, right? So of course, analytical really doesn't seem important. So we would say maybe not serious. But is there anything about this derived intersection, like Serre conjecture, taking into account this derived things, derived fixed point?
I've never thought about it.
People thinking of maybe some p-adic cohomology, or I don't know, some invariant, taking into account that it's not reasonable just to take the naive intersection.
Mm-hmm.
Nowadays,
Yeah.
So, but no idea, just vague speculations.
Yes.
But here, what is the derived intersection here? There is no...
Well, it's a derived scheme, right?
Which one?
X.
I mean, x was x over x was x, so by the two maps. So you take the derived intersection.
X cross...
This X sigma.
No, but X sigma...
But it was x was x over the two maps, so you can take the derived thing.
No, but it is equal, because here it is a complete intersection situation. It's not...
Is it?
It's not... you just have... the number of the codimension is a number of equations, and there is no.
In this case.
In this case, it's by assumption. It's just
Maybe no difference.
Okay. Thanks for answering for me.
Yeah, I have just a question about Katz-Lomon. So you are in the general case, not in the curve case. So is there a reduction to the Katz-Lomon? Katz-Lomon is about curve case. So what do you mean by Katz-Lomon?
But by Katz-Lomon, I'm saying that this this nearby cycle of this guy, at zero is zero. Yeah, this is. So I have a map from here to some. And I import this Katz-Lomon by pullback or something. Yeah, smooth base change, plus smooth base change, yes.
We're out of time, so let's thank the speaker again.